Application to public good cost sharing. Consider a group of n agents who have access to a machine that can convert their labor into some public good. Specifically, suppose that the machine requires the simultaneous labor of all n agents in order to work. The agents are free to jointly decide how many hours of labor L to work. Implicit is the requirement that each agent work for L hours. However, since the machine requires all n agents' labor simultaneously, after L hours of labor, the machine outputs Y equals to capital Y of L units of some public good, where the production function Y, capital Y, is assumed to be an increasing and strictly concave function, with Y of 0 equals to 0. Different agents may have different preferences over how much labor they should provide in exchange for the public good. Let us suppose that we know something about their preferences, other than the fact that they are represented by some utility function, Ui of Ly, which is strictly increasing in Y, strictly decreasing in L, and is quasi-concave. See figure 10.3. In this environment, a rule takes as input the reported utility functions of the agents, subject only to the assumptions we have made. It then gives as output a single labor requirement L equals to F of U1, U2, U3 until Un. Each agent is then required to provide L units of labor, and they enjoy Y of L units of output as a reward. What rules are strategy proof and onto? By assumption, outcomes may only be attained along the graph of Y because of the assumptions on Y and on preferences. It is clear that agents have a single picked preferences over this consumption piece. It follows that any strategy proof onto rule for this environment is a generalized median voter schemes operating along the graph of Y. Proving this is not difficult, but it involves some technical details that we omit. First, the outcome space is not bounded as we assumed before, although it would certainly be reasonable to bound it by assumption. Second, the preference domain here should be verified to yield all the single-picked preferences necessary to characterize generalized median voter schemes. E.g., we used the symmetric single-picked preferences to construct the proof of theorem 10.2. Third, one should demonstrate that a strategy proof rule in this environment is invariant to utility information away from the graph of Y. We leave it to the interested reader to verify our claim despite these technicalities. In this kind of problem, it may be reasonable to add additional requirements to a rule. One that we address is the requirement that an agent should be better off as part of this decision-making group than if he were simply to walk away. Formally, if this public good technology did not exist, each agent would provide no labor, L equals to 0, and would enjoy none of the public good, Y equals to 0. We say a rule is individually rational if for all capital U, which is this collections of tuples, U1, U2, U3, and so on to Un, and 1 is greater than equals to I, greater than equals to N. No, 1 is less than equals to I, less than equals to N. There's a typo. We have Ui of f of U, Y of f of U is greater than equals to Ui of 0, 0. What strategy proof and onto rules satisfy individual rationality? In terms of our earlier model, where agents have a single picked preferences On the unit interval, that question translates as follows. What GMBS has the property that, for any preference profile, each agent weakly prefers the chosen outcome to the outcome x equals to 0? The answer is that there is a unique such rule. As an exercise, we leave it to the reader to show that the rule that chooses the minima peak is the unique strategy proof onto rule that satisfies these individual rationality conditions. In terms of this public good model, this corresponds to asking each agent their most preferred labor level L and choosing the minimum.